to Dave's Think Tank. I've told you before about the Vector. This machine has hardly ever given me a moment's trouble. All the circuit boards are still original. Most have never even been removed. The displays are all original. The playfield paint is still original, except for a very few spots that I've touched up just recently. It's still on all incandescent bulbs. As for this machine, I've never felt the need to go to LED. So if I'm ever going to do a video about the Vector, it's going to have to be on preventive maintenance. Okay. I like the design of this back box. You don't have to take the glass off to get into it. I've actually done 2 preventive maintenance videos on this machine. One, I took the battery off of the MPU board, replaced it with a memory capacitor. The other, I put a Mylar, custom fit Mylar to the upper play level here, and that's working out very well, by the way. I'm very happy with that. Today I want to look at the voltage regulator board. And one of the first things you see when you look at this, oh, let's get a little light on it. Hopefully that's better. So one of the first things you're going to notice is there are 2 huge capacitors here. And they are principal components of the voltage regulation system. This one is part of the 5 volt. It takes 12 volts coming in, converts it to a nice smooth 5 volts. This one takes 240 volts coming in and converts it to about 190 or less. You can set it down a bit with this adjuster here. So the 5 volts is used throughout the whole machine for every computer chip. Every single board receives 5 volts. Every single board has computer chips. This one controls the displays. The 190 volts controls the displays. So if either of these goes bad, you could have a lot of expensive damage. I've owned this machine for 20 years now, and I have never replaced either of these. And looking at them, I'm pretty sure whoever owned them for the previous 20 years never replaced them either. This company that made this one, they went out of business in 1985. It is recommended in some places that these be replaced every 10 years. So I'd say we're long overdue. So the first thing we want to do is get some initial voltage readings from the board. So get your multimeter and set it on DC. We're going to take the black lead here and slip it underneath the braided ground wire at the bottom of the board. Get in there. There we go. Now we're going to test TP5. That is the incoming 12 volts. And we've got 13.13. I don't know if you can see that, but 13 is not too bad. Let's test TP1. This is after it's been regulated to 5. Oops, we have 5.32. Not bad. TP3 should be the same voltage. And it says 4.8, 4.9. Huh. It's interesting. Okay, TP4 is incoming 240 volts, so be very careful when you're reading this one. 225, so that's pretty good. And TP2 is the regulated 190. It's set to 179.8. Okay, so that has been adjusted down. And the reason you would adjust it down is this controls the displays. And if the displays are done at too high a voltage, they can burn out. So if you're only going to keep it for 10 years in your arcade, yeah, you don't mind if the displays burn out. If you're trying to keep it going after 40 years, you want to turn it down just a bit. The difference is imperceptible. Okay, so let's pull out the board and get started. So I have here my capacitance meter. I bought this last week specifically for this purpose. It was $18 on Amazon. I also have my replacement capacitors purchased online from mouser.ca, mouser.com if you're in the States. When specifying the capacitors you want, it's okay to go up in voltage. Capacitance is a bit more important to keep close to the original, although you can go up a bit in capacitance as well, as it looks like they used underpowered capacitors in building these games, likely to save some money. So people have been replacing this one, which is 11,000 microfarads, with this one, which is 15,000 in most of the videos that I've seen. So let's measure the capacitance on these as we're going to be putting them in the game. Make sure that they work. So this one is 15,000. I'm going to set this to 20,000 and turn it around that way. I'm going to put the negative lead on the negative, positive lead on the positive. And what do we get? We get 1350, around 13.5. So it's supposed to be 15,000, it's 13,500, but it's a lot better than the previous one. So how about this one? We're replacing this one here. It's 160 and 50 volts. We are replacing it with 180 and 160 and 350 volts. We're replacing with 180 and 350 volts. The voltages is the same. So let's set this, we have to set this back to 200. Set this to the closest number, so 200 is closest to 180. And put this on the negative, this one on the positive. And we got 168.8. So this one's a bit low as well, but still above the specifications. Now I also bought this. If you can see that, the three of these are often sold as a kit to upgrade your board. So why these three? I assume because they're all aluminum electrolytic capacitors. The active components in each of these are aluminum and electrolytics. Electrolytes dry out after a few years, they leak out, they cause all kinds of trouble. So to be on the safe side, I'm going to replace all three. So I'm replacing this one here is 2 microfarads, 25 volts, and I'm replacing it with this is 2.2 microfarads and 50 volts. So let's just get a measurement on it, and negative is this side, so positive is this side, and we're getting exactly 2.2, so this one is exactly what we paid for. So the first thing we're going to do, I'm going to discharge these capacitors. I doubt they have any remaining voltage in them, but just in case, we're going to discharge them, and the way we do that, we get a nice big resistor, and this is the biggest resistor I've got. It's on an old board, but it doesn't have to be removed. And what we do is we attach this to the capacitor for about 5 seconds, and that should drain all the power into that resistor. So just count to 5 slowly. Okay, now we'll do this one. And yep, let's get where you can see it. Count to 5. Okay, and that should be dry now. And let's check this one as well. Okay, there should be no remaining power in any of those. Next we have to take off the old capacitors and replace them. So I'll come back when that's done. So this is interesting. I had to check this out, but on this capacitor that I'm going to be removing, it has a capacitor soldered to it, which is a little odd. And so I checked on the schematics, and the schematics say, yes, there should be a capacitor there, but it's not set up the way you would expect, going through holes on the board. So I got out my old Flash Gordon, which I replaced previously, and here is the same capacitor that we're going to replace, and it has a capacitor with holes on the board. So this is a later model, and somebody at some point decided they liked that model and they wanted to add this capacitor. I'm not sure what problem it solves, but somebody thought it was important enough to solder one directly to the leads of this capacitor. So we'll be putting that back in. So that is done. And because nothing ever goes easily, I had to drill the holes bigger to fit these ties through. But other than that, things went okay. I've got this one connected to the original 2 wires. This one used to fit in like that, a wire over here, a wire over here. I've connected the wires under the board and brought them up on top through the holes. This one is here with its extra side capacitor. And what we can do now, we can just measure these old capacitors, find out how good they were. So this is supposed to be 160. Let's see what it says. 192. Okay, so that was still in good shape. This one's supposed to be 11,000. Okay, oh, that's the positive there. And it's fluctuating 9, 8, 10. Okay, this may have had some problems. And this little one here is supposed to be 2. Oops, have to recalibrate that. 2.6. Really? So it's doing very well as well. So, for being 45 years old, that's not too bad. Now, while I've got the board off, there are a few changes that are recommended. Modifications that people have discovered over the years that improve the performance. This is the negative coming off the capacitor, the 15,000 we just put in there. And you see it follows this line over to a single pin here. So it takes power back to the rectifier board through a wire connected to a single pin. So that puts a lot of strain on that single pin when there's all kinds of negative things going back, taking negative power back to the rectifier. And there's one right below here which connects up to, right here. And it follows around a path around here, and it takes negative power throughout the whole board around the edges. So what we're going to do, we're going to scrape off a little of the green here, and we're going to make a solder bridge from there to there, and that will improve the resilience, particularly of that pin right there. The same thing. Here's the back of the board where I put the black and the red, the negative and the positive. The negative here as well, it comes around here and it hooks up to a single pin. So a lot of strain on that pin, where we could just jump it. We'd have to jump it with a wire, take it from here over to the edge here, and then we'll have a lot better flow. Now the other thing, okay, we've got touch point 1 that we used earlier, right here, supposed to be 5, and touch point 3 down here is also supposed to be 5 volts, that is. And the reason they are the same is because touch point 1 goes directly to a connector, and a wire from that connector goes directly from this pin over to this pin, and then goes into TP3. So why the power goes off the board and then comes back on the board and then goes into this line, I don't know. They made some compromises in the design, but we can improve on that by just having a wire straight from here over to here, making sure that the various that the 5 volts goes directly there. As we noted before, I think TP1 was around 5 volts, TP3 was around 4.8. So in going through that that external connector and through that wire and 2 connections, it somehow is not connecting up properly. So we can take a wire straight from there to there. So I'm going to do those 3 things and come back to show you those. Okay, so those 3 jobs are done. I have scraped a bit of the coating off here and connected a wire across here, so that's connecting the capacitor ground to the board ground. Same here, this capacitor ground is connected around to this ground for the board. Over here I have TP1 connected directly to TP3, and everything should be good. Okay, just a couple of tests we can do. Check our work. Put your multimeter on continuity so we get a beep if we have a connection, so we can test if we have a connection from ground to this capacitor. And we do. And do we have from ground to negative on this capacitor? Yes, we do. And do we have a connection from TP1 to TP3? Okay. Now I think we're ready to reinstall. Well, the job is done. The board's installed. I've only connected J3, the power cable, takes the power connector, takes the power to the 240 and the 5 volt that we have just put together. So let's try turning it on. Okay, some things are working without power from the regulated power board, but here I'm going to set this on DC, put the negative under the ground braid, and let's check power coming in. TP5 is 13.2, 13.3. So that's okay. Hopefully it's the same as before. I'll have to double check that. Now TP1, 5.18, 5.19. Rock steady, so that's good. And TP3, it's also 5.18, 5.19. So that's great because we connected that wire to make sure that they would be exactly the same, and they are exactly the same. Now let's check out, what do we have here? TP2. That is 224 volts coming in, 225 volts coming in. Oh, sorry, that's TP4. And TP2 is our regulated 179. Okay, so I think it's perfect. Everything is working as expected. Well, I've got all the plugs in, back in place, and let's turn the machine on, just make sure everything works the way it's supposed to. Okay, sounds good. Lights flashing, voice good. I think everything's back to normal. So, let's play a game.
Vector, I am up. Play analysis computer. Your vector plan. Defenders down. Shoot for vector scan. Good. In position. Great shot. Soar. Vector. Z. Break. Set. Release. Do play. Shoot torque. Gas. Why?